So think about this for a second. How does your computer actually manage to organize and retrieve thousands or even millions of files almost instantly, without bogging down? I mean, you click a folder and boom, everything is just right there. It feels like magic, right? But it's actually driven by a very specific, incredibly elegant mathematical architecture.
The secret behind that blistering speed is a nonlinear, hierarchical data structure called a tree. Unlike a flat list of data where your computer literally has to scan items one by one, a tree branches out. A file system starts at a single home point and then branches down into specific directions and subdirectories. It really is an elegant, foundational solution for efficient searching and data storage in everyday computing.
Welcome to today's Explainer, everyone. Today, we are going to demystify the tree data structure. We're going to take what can sometimes feel like an intimidating, heavily academic concept and transform it into a logical, highly useful tool that you can completely wrap your head around. Here is our agenda for this explainer. First, the anatomy of trees. Second, a focus on binary trees. Third, core binary tree operations. Fourth, navigating with tree traversals. And fifth, performance and complexities. Okay, moving into Section 1, the anatomy of trees. Let's establish our foundational vocabulary.
Basically, a tree is a hierarchical data structure composed of nodes that are connected by edges. The absolutely crucial point to grasp here is that, much like a linked list, a tree doesn't have a strict upper limit on the number of nodes. Because these nodes are dynamically linked using memory pointers, rather than being packed into a fixed rigid array, a tree can grow as large as your computer's memory allows. Think of it less like an ice cube tray with a set number of slots and way more like a living vine that just keeps sprouting new leaves.
Let's quickly map out this anatomy. At the very top, level 0, we have the root node. From there, everything flows downward. Internal nodes that branch out further are called parents, and the nodes directly below them are, you guessed it, their children. Nodes that share the exact same parent are siblings. And finally, at the very bottom, nodes that have 0 children are called leaf nodes or terminal nodes. Section 2. Focus on binary trees. Let's zoom in on a very specific building block.
In a binary tree, things get beautifully restricted. A parent node is strictly limited to having a maximum of 2 children. You don't ever have to worry about 3, 4, or 50 branches coming off a single point. It's strictly binary. We simply categorize these 2 potential children as the left child and the right child.
At the code level, there really is no magic happening under the hood. A node is just a simple data package, a C++ struct, for example. In the center compartment, you have the actual data being stored. Flanking that data on either side are 2 pointers, one holding the memory address for the left child and the other holding the memory address for the right child.
And here's how those individual structures link up. Starting from the main root pointer at the very top, the root node uses its left pointer to connect to a left child and its right pointer to connect to a right child. If a node doesn't have a child in a particular direction, that pointer just points to null. It's essentially a graceful chain of addresses building out a vast hierarchy.
Moving on to Section 3, core binary tree operations. Let's see how we actually modify these structures.
The operations in a binary search tree are governed by crisp, recursive logic. Whether you're searching or inserting, the rules are exactly the same. You look at the current node. If your target value is smaller than the node's data, you go left. If your target value is larger, you go right. And if the spot you land on is entirely empty, meaning it's null, that's exactly where you insert your new node.
Let's trace a search together. Say we're executing a search for the number 19. We start at the root, which is 18. Since 19 is larger than 18, the logic says, go right. Now we're at 23. Since 19 is smaller than 23, we go left. And boom, there it is, node 19. We found our data in just 3 simple comparisons, completely ignoring the entire left side of the tree. That is the sheer power of this structure in action. Now, while insertion and searching are a breeze, deletion is uniquely tricky. When you remove a piece from the middle of a structure, you have to patch the hole. If you delete a leaf node with 0 children, easy, just remove it. If it has 1 child, you just bypass it. But if the node being deleted has 2 children, you suddenly have a succession crisis. You have to carefully find the minimum value in its right subtree to replace it. This ensures the strict left is smaller, right is larger rule remains completely unbroken, which keeps the whole family tree from falling apart. Section 4. Navigating with tree traversals. How do we systematically visit these nodes?
Once your tree is perfectly built, you need a systematic way to visit all the nodes, maybe to print them out or copy the structure. We have two main navigation strategies for this. The first is depth-first search, which uses recursion to dive deep down the branches. This comes in three flavors: in-order, pre-order, and post-order. The second strategy is breadth-first search, or level-order traversal, where we scan broadly, level by level, using a queue.
To really contrast these two approaches, think about their behaviors. A depth-first search immediately plummets down the left side, exploring vertically as far as physically possible first. Breadth-first, on the other hand, strictly reads left to right across each horizontal tier. It hits the top level, then the entire next level down, then the bottom level. It's a fundamental difference in how we traverse the data.
Let's break down those depth-first flavors. An in-order traversal visits the left subtree first, then the root itself, then the right subtree. If you run this exact sequence on a binary search tree, something wonderful happens. It perfectly outputs the nodes in ascending, sorted numerical order. It's incredibly satisfying.
Compare that to a pre-order traversal. Here, we visit the root node first, then the left, then the right. Because you are capturing the parent node before its children, pre-order is absolutely the ideal algorithm when your goal is to create an exact architectural copy of the tree, or when you need to generate a prefix expression. And wrapping up our depth-first trio, we have the post-order traversal. This one goes left, then right, and saves the root for absolute last. This means it processes the leaf nodes at the very bottom first. This is a highly useful trait when you need to safely delete an entire tree from your computer's memory. You delete it from the bottom up, ensuring you never pull the rug out by deleting a parent while its children are still relying on it.
Finally, Section 5, Performance and Complexities. Let's talk about Big O.
The absolute most crucial takeaway regarding performance is the stark difference between average and worst-case scenarios. When a binary tree is well-balanced, it gives you incredibly efficient operations at big O of log n. Every single step cuts the remaining data in half. But if you just lazily insert already sorted data, like 1, 2, 3, 4, 5, you create what's called a skewed tree. It essentially becomes a single long diagonal branch. At that point, your performance degrades terribly to big O of n, making your fancy tree no better than a slow linked list.
Let's bring all this theory into the real world with a practical application. We can represent the mathematical equation x equals a plus b minus c times d strictly as a hierarchical tree structure. The operators, like minus, plus, and multiply, act as the parent nodes, while the actual variables, a, b, c, and d, sit safely at the bottom as leaf nodes.
Which brings us to a final provocative challenge for you. Based on everything we've uncovered today, which of our three depth-first traversals, in-order, pre-order, or post-order, would generate the prefix notation, the infix notation, or the postfix notation for this exact equation? As a hint, really think about exactly when the operator, parent node, gets visited. Thank you so much for joining me on this explainer. I highly encourage you to grab a piece of paper and try mapping that equation out for yourself.